In a perfectly balanced linear electrical load, the neutral conductor ideally carries no current. This occurs because the currents flowing in the ungrounded or hot conductors effectively cancel each other out within the neutral conductor. Imagine a simple scenario with two hot wires, each carrying 20 amps of current, and a neutral wire. If both hot wires supply identical loads, the current returning through the neutral from each hot wire is equal and opposite, resulting in a net current of zero in the neutral. However, real-world electrical systems rarely exhibit perfect balance. Various factors contribute to load imbalance, including differing appliance usage patterns, variations in lighting loads, and the inherent characteristics of certain electrical devices. This imbalance introduces current flow in the neutral conductor. The magnitude of this neutral current directly correlates with the degree of load imbalance. A greater imbalance leads to a larger neutral current. The National Electrical Code, commonly known as the NEC, sets forth the standards for safe electrical installations. It mandates that the neutral conductor must be sized to safely accommodate the maximum potential unbalanced load. This requirement dictates the permissible reduction in size of the neutral conductor compared to the ungrounded hot conductors. The provision allowing the neutral conductor to be equal to, or no less than 2 sizes smaller than the ungrounded conductors represents a carefully considered balance between safety and economic considerations. Increasing the size of the neutral conductor enhances safety by providing a greater capacity to handle unbalanced currents and minimize voltage drop. However, larger conductors also entail higher material costs and installation expenses. Conversely, decreasing the size of the neutral conductor reduces cost but compromises safety by increasing the risk of overloading the conductor and causing excessive voltage drop. The NEC allowance for a 2-size reduction in the neutral conductor strikes a reasonable compromise. It ensures that the neutral conductor possesses adequate capacity to handle the typical maximum unbalanced load encountered in most applications while remaining economically feasible. This approach recognizes that perfectly balanced loads are unattainable in practice and accounts for the inevitable presence of some degree of imbalance. To delve deeper into the specifics, consider the requirements outlined in NEC Section 220.61. This section provides detailed guidelines for calculating the neutral conductor load for services. It acknowledges that for ranges, dryers, and similar appliances, a demand factor of 70% can be applied. This recognizes that these appliances rarely operate at their full rated capacity simultaneously. Furthermore, the NEC permits a reduction in neutral conductor size for feeders supplying electric ranges, wall-mounted ovens, counter-mounted cooking units, and electric dryers, as specified in Section 220.61 Burn-in 220.61b2. The code also addresses situations where the major portion of the load consists of nonlinear loads, such as those found in electronic equipment, computers, and fluorescent lighting with electronic ballasts. These nonlinear loads generate harmonic currents, particularly the third harmonic, which are additive in the neutral conductor. In such scenarios, the NEC mandates that the neutral conductor be sized to carry the maximum unbalanced load, including the harmonic currents. This may necessitate increasing the neutral conductor size beyond the standard 2-size reduction. For example, if the ungrounded conductors are rated for 100 amps, a neutral conductor 2 sizes smaller would typically be rated for 70 amps. However, if the load consists primarily of nonlinear loads with significant harmonic currents, the neutral conductor might need to be sized at 100 amps or even larger to safely handle the increased current. Let's consider some practical examples. Imagine a residential service with two 200 amp hot conductors. According to the NEC, the neutral conductor could potentially be 2 sizes smaller. However, it's crucial to consider the specific load characteristics. If the home primarily uses incandescent lighting and traditional appliances, the load is likely to be relatively balanced and contain minimal harmonic currents. In this case, a neutral conductor 2 sizes smaller might be acceptable. On the other hand, if the home is equipped with numerous electronic devices, energy-efficient lighting with electronic ballasts, and other nonlinear loads, the harmonic currents could significantly increase the neutral current. In this scenario, it would be prudent to use a neutral conductor that is the same size as the unrounded conductors, or even larger, to ensure adequate capacity and prevent overheating. In commercial buildings, the potential for unbalanced loads and harmonic currents is often greater than in residential settings. Office buildings with extensive computer networks, data centers, and fluorescent lighting systems are prime examples. In these applications, careful consideration must be given to the neutral conductor sizing. It's often necessary to perform detailed load calculations and harmonic analysis to determine the appropriate neutral conductor size. In some cases, it may even be necessary to install oversized neutral conductors or dedicated neutral conductors for specific circuits to mitigate the effects of harmonic currents. The NEC provides additional guidance on neutral conductor sizing in various articles and tables. Article 310 addresses conductor ampacity and includes tables that list the allowable ampacities of different conductor sizes and types. These tables take into account factors such as conductor material, insulation type, and ambient temperature. Article 220 provides detailed requirements for calculating branch circuit, feeder, and service loads. This article includes specific provisions for calculating the neutral conductor load, taking into account factors such as load type, demand factors, and harmonic currents. It is important to note that the NEC is a minimum standard, and in some cases, it may be necessary to exceed the code requirements to ensure safety and reliability. For example, in critical applications such as hospitals and data centers, it is common practice to install oversized neutral conductors and grounding systems to minimize voltage drop and prevent equipment malfunction. The concept of voltage drop is closely related to neutral conductor sizing. Voltage drop refers to the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction, reduce the efficiency of lighting systems, and even damage electrical components. Increasing the size of the neutral conductor reduces its resistance, which in turn reduces voltage drop. Therefore, when designing electrical systems, it's important to consider both the ampacity and the voltage drop requirements of the neutral conductor. In addition to the NEC, other standards and guidelines may also apply to neutral conductor sizing. For example, the Institute of Electrical and Electronics Engineers, known as the IEE, publishes various standards related to power quality and harmonic mitigation. These standards provide guidance on how to minimize the effects of harmonic currents on electrical systems, including recommendations for neutral conductor sizing and grounding practices. Furthermore, local codes and regulations may impose additional requirements for neutral conductor sizing. It's essential to consult with local authorities and qualified electrical engineers to ensure compliance with all applicable codes and standards. In summary, the NEC provision allowing the neutral conductor to be smaller than the ungrounded conductors represents a carefully considered balance between safety, cost, and practical considerations. The code recognizes that perfectly balanced loads are rarely achievable and allows for a reduction in neutral conductor size provided that the conductor is adequately sized to handle the maximum potential unbalanced load. However, it's crucial to consider the specific load characteristics, the presence of harmonic currents, and voltage drop requirements when determining the appropriate neutral conductor size. In applications with significant nonlinear loads or critical power requirements, it may be necessary to exceed the NEC requirements and install oversized neutral conductors to ensure safety and reliability. Always consult with qualified electrical engineers and adhere to all applicable codes and standards to ensure the safe and proper installation of electrical systems. The neutral conductor plays a vital role in maintaining the integrity and safety of electrical systems. Proper sizing and installation of the neutral conductor are essential for preventing overheating, minimizing voltage drop, and ensuring the reliable operation of electrical equipment. By understanding the technical reasons behind neutral conductor sizing requirements and adhering to the guidelines outlined in the NEC and other relevant standards, electrical professionals can design and install safe and efficient electrical systems to meet the needs of a wide range of applications. Remember to always prioritize safety and consult with qualified experts when making decisions about neutral conductor sizing and electrical system design. The potential consequences of undersized neutral conductors, such as overheating, equipment malfunction, and even fire, can be severe. Taking the time to properly assess the load characteristics, consider the presence of harmonic currents, and adhere to the applicable codes and standards is a critical investment in the safety and reliability of electrical systems. Finally, ongoing education and training are essential for electrical professionals to stay up to date on the latest codes, standards, and best practices related to neutral conductor sizing and electrical system design. The electrical industry is constantly evolving, with new technologies and materials emerging regularly. By staying informed and continuously improving their knowledge and skills, electrical professionals can ensure that they are providing the highest level of service and expertise to their clients. The seemingly simple question of why the neutral conductor can be 2 sizes smaller than the unrounded conductors actually opens up a complex and fascinating world of electrical engineering principles and code requirements. Understanding these principles and requirements is essential for anyone involved in the design, installation, and maintenance of electrical systems.